Hello. Today, I'd like to talk about Section 11.2, which is the properties of power series. So this is a continuation of what we did last time, where we had these polynomials that were estimating functions. Now what we want to do is we want to say, well, actually, we can maybe take those polynomials as being infinite dimensional, or infinite degree polynomials. So you're taking an infinite number of terms, and then you're looking at the power series that's defined by that, which we can then say some stuff about. So that's what we're going to talk about today. So the first thing I want to talk about is sort of some terminology for this. The center of the power series is the A, where the power series is defined as x minus a to the kth power. And so you can sort of center the power series about different points if you want better convergences at different points for the function. And so that's the idea, is that you sort of take a center of the power series, and then you look at that as the convergence is going to happen around that central point of the x values there. So that's the center of the power series. The set of values for x where this is a convergent sequence is called the interval of convergence. And so what we're going to see is that center is right in the middle of that interval. And then on either side of the interval, you've got endpoints. And those endpoints might be infinity and negative infinity. If that's the case, then this sort of converges everywhere. And it might be that you have sort of an r and a minus r for convergence here. And so what you will actually see the convergence depend on what value of x you plug in, which makes a lot of sense, right? Because you're sort of looking at this thing. This is basically a geometric series to some degree, ignoring the fact that CK might have some Ks in it. So it's basically a geometric series, and that geometric series may or may not converge everywhere. So you sort of think of, like, you know, if that thing inside of there is less than 1, it's going to converge. If that's bigger than 1, this is going to diverge. So you might see that as what's happening here. All right, that's the interval of convergence. The radius of the convergence is the distance from the center to the boundary of that interval of convergence. So you can sort of think like the center is right here in the middle, and then on either side you might have like a plus r and like a minus r. And so then those two endpoints would be the endpoints of the interval of convergence. R in there is the radius of convergence. So that's sort of just a definition. All right, so what we have now is we sort of say we can have this convergence. It converges in one of 3 ways. So the first way is that it's convergent everywhere. So the interval of convergence is minus infinity to infinity, and the radius of convergence is r equals infinity. So these sort of converge everywhere functions are going to have some k values in that c sub k. So you're going to see some of that in there. One of these that we did last time as a sort of finite polynomial, the sine function actually ends up being one of these that converges everywhere because the sort of power series is outweighed by the k factorial in the denominator of that sum there. And so you sort of, when you're doing the sine function, the sine has a k factorial in the denominator, and that's going to kind of outweigh the x minus a to the k for any x I plug in. And so then this thing is going to go to 0, and it's an alternating series, so that every other term is plus and minus. It's only the odd terms of this series, and so it's actually going to converge everywhere. That's kind of nice. It's possible that the second sort of way it converges is there's a number where it's sort of convergent, absolutely convergent, if it's less than this r, and divergent when it's greater than r. And then on the endpoints, I need to check those 2 endpoints as well. And so you sort of have this radius of convergence is r, and the interval of convergence is either sort of minus r to r, not including either one, or maybe I include one but not the other, or maybe I include both. And so what has to happen is I have to check the endpoint for convergence to see whether it converges at either endpoint, and that's sort of I have to check. And then finally, the last way this converges is it maybe only converges when x equals a. Okay, now it always will converge when x equals a, because every term in this series will just be 0 times c sub k, and whatever c sub k is, that's just going to give me 0. So that will always be convergent, but potentially maybe it only converges there. Everywhere else is divergent, and that's possible. That's a possibility. All right. So let's look at an example of this. So for an example, let's look at x minus 2 to the k over the square root of k. Okay, so I want to find the radius and interval of convergence for this series. So the way that we're going to do this is we're going to say, let's try to see if the ratio test or the root test will give us this interval of convergence. And so we're going to take the ratio test. So I want to take the k plus first term of this sequence, which is the top here, and the kth term of this sequence and divide the two. Then take the absolute value and do the limit as k goes to infinity. Okay. So this basically just turns into, limit k goes to infinity, absolute value of x minus 2 to the k plus 1 over square root of k plus 1 times square root of k on top over x minus 2 to the k on the bottom. Okay, and so I sort of have this on the next slide. It's basically looking at this. I can divide out that x minus 2 to the k. It goes away, and I just get an x minus 2 left over, and I have square root of k over square root of k plus 1. As k goes to infinity, the square root of k over k plus 1 goes to the square root of 1, which is just 1. So I end up with x minus 2. So the question here is, all right, what does that mean? I did the ratio test. The ratio test says this is convergent when r is less than 1 and divergent when r is greater than 1. Okay, so that means that really this x minus 2, which is really an absolute value here, needs to be less than 1, which getting rid of the absolute value here means x minus 2 is between -1 and +1. And so then I actually get that x is less than 3 and greater than 1. So somewhere between 1 and 3 is sort of a guaranteed absolute convergent sequence. So I have that. Now I also have to check the endpoints here. So I get 1 and 3, but then maybe at 1 it converges and at 3 it does not, or maybe at 3 it converges and at 1 it does not, or maybe they converge at both. And so we have to do a little bit of work here. So we check x equals 1 and x equals 3 separately. So I plug x equals 1 into my original series. So I plug 1 in, 3 in. So I'll plug in 3 in first. 3 minus 2 is 1. 1 to the kth power is 1. And so I have 1 over the square root of k. And we looked at this before, but I'll sort of re-emphasize this. This, if I integrate it, and I sort of think of it as a function, x to the minus 1/2 dx. The integral of this thing between 1 and infinity, or really 1 and n, and the limit as n goes to infinity, is just going to be 2 times the square root of x, evaluated between 1 and then n goes to infinity. And so this is actually infinity, so it's not convergent. So this sequence diverges by the integral test. And in particular, we can even say more. It's a p series with p equals 1/2. And if p is 1/2 or lower, or actually if p is 1 or lower, this is a divergent sequence. And so this p series does not converge. On the other hand, if I plug 1 in for x, I get -1 to the k over square root of k. By the alternating series test, all I need is that 1 over square root of k goes to 0 in order for this to converge. And so I look at this thing and I say, all right, so the 1 over the square root of k part, as k goes to infinity, it does converge to 0. Therefore, this series actually converges as well, because it's alternating, and in an alternating series test, all I need to check is that the inside term goes to 0 as k goes to infinity. And so I get this convergence by the alternating series test. So you can see we have a convergent sequence when x is 1, and a divergent sequence when x is 3. So the interval of convergence here is going to be including 1, not including 3. The center is 2. The radius of convergence is just 1. So 2 to 3, 2 to 1, is there's 1 in between each of those. Okay. So in order to do this determining of the radius of convergence, I'm going to use the ratio test or the root test that finds an interval where the series is absolutely convergent. So everything in between those two values is absolutely convergent. So the absolute value of that series is a convergent series. And that's the radius of convergence is just going to be what R value I add to this. I've got these backwards for some reason. So I got A minus R on the left, A plus R on the right is what I should have. All right. So it's A is the middle, A minus R, A plus R. That R is the radius of convergence. And then the interval of convergence, I need to actually check the end points of that interval. And so either I've got like everything. So if the radius of convergence is infinity, my interval of convergence is minus infinity, infinity. If I've got 0, radius is 0, then the interval of convergence is just x equals A. And if I'm between 0 and infinity, so I'm not infinity, I'm not 0, I'm finite, this interval of convergence is this interval, or maybe the including left endpoint, not including right, including both endpoints, not including left, including right. So it's sort of like you got to check the endpoints to determine whether it's convergent at the endpoints as well. Okay. So what I can do now is I say, all right, so now there's all sorts of rules that I have for convergence of other power series. So if I have found the interval of convergence for 2 power series and they match, or in particular, if one is a subset of the other. So if one interval is inside of another interval, I take the smaller interval and they both converge on that smaller interval. So if these 2 power series converge to f of x and g of x respectively, so 2 functions here, the sum and the difference for these 2 power series, so the sum of ck plus dk or ck minus dk, is just the sum or the difference of the functions f of x and g of x on that same interval I. So adding and subtracting these things, I get to sort of say, well, those actually still converge to the sum and difference of what the functions were that they converges to. All right. Multiplication, I can actually multiply these things by a power. So it's sort of a little bit tricky, but when I have an integer with the property that m plus k is positive for all terms inside that power series, then I can sort of multiply that m plus k inside of that power series. It converges to x to the m times the original function f of x when x is not 0 on the interval. When x is 0, we actually converge to the limit of this function x to the m times f of x. So at 0, if at 0 f of x goes to infinity, say, I'm going to need to do like a L'Hopital's rule kind of trick to figure out whether this is convergent at that 0, x equals 0. And also you'll notice this is actually kind of a little bit weird, but outside of that interval, you might have that 0 that's outside that interval as well. Okay. Finally, if I have an h of x, which is b x to the m, and m is a positive integer, b is a non-zero real number, then I can sort of take a power series of h of x to the k. So I replace my x in here with h of x to the k, and this is going to converge to the composite function f of h of x for all x to h of x is on the interval. So now this is a little bit tricky, but basically, the nice thing that we get out of this is that we get to combine these power series and maybe find a power series for something that you don't know how to find it of before. So in particular, I have the power series for the geometric series. So the geometric series is just straight up ones as coefficients of this power series. It will converge when the absolute value of x is less than 1. When the absolute value of x is equal to 1, when it's 1 or negative 1, this is not a convergent sequence. So when it's 1, it just diverges to infinity. When it's minus 1, it just bounces between the sort of adding and subtracting 1. And that doesn't go to 0. So it's an alternating sequence that doesn't go to 0. It's not going to be a convergent sequence. All right, so this is sort of what we know so far. We can find then the power series expansion of x to the 5th over 1 minus x. Okay. All I need to do is multiply both sides of this equation by x to the 5th. Now, x to the 5th is one of these, it has the property that it's positive, and 5 plus k is positive, or really positive for any k that I have from 0 to infinity. So this thing is going to satisfy that property that we had in the last slide here. So I sort of think about this. It's a sum of x to the fifth, x to the sixth, x to the seventh, and so on. And I don't have an x to the sixth in there, but that's all right. And so I have x to the k plus 5. This will still converge for absolute value of x less than 1. And so you sort of think like, it's going to converge on that same interval. And it's convergent to, in fact, this sum x to the k plus 5. So this sum is convergent to that function. So the function x to the fifth over 1 minus x has a power series expansion, sort of an infinite polynomial expansion of this thing, as x to the k plus 5 in there. Okay, so that's helpful. So I can do a lot with this, really. So think about this, another one. I have 1 over 1 minus x. So I'm taking x to the k again is the series. It's convergent for absolute value x less than 1. And I can now sort of think about, what about 1 over 1 minus 2x? Well, 1 over 1 minus 2x, I plug 2x into the x inside of my power series here. So what do I get? It's 1 plus 2x squared plus 2x cubed and so on. That's just 2x raised to the k power. And that will converge when the absolute value of x is less than 1/2 between negative 1/2 and positive 1/2. And you'll notice at the endpoints, I again can go do this check, but the endpoints would be the same as plugging 1 and minus 1 into the original function. So when I plug 1 into the original, I don't have convergence. Minus 1, I don't. Plug 1/2 in, I get 1 when I multiply. It's not convergent. Negative 1 when I plug in, and it's still not convergent. So I don't have convergence at either endpoint, but everything in between, I have convergence for this one. Okay. So last but not least, we can do some stuff with these as well that are kind of weird. We get to differentiate and integrate these power series. So I have a power series here, x minus a to the k with the ck, and it's convergent for x minus a less than r. So it's convergent on this interval, and it defines some function f of x on that interval. Well, to take the derivative of f of x, I can do that. It is differentiable. It's a differentiable function, implying it's also continuous. The derivative is found by just differentiating the power series. So I take the derivative of each term in here. The only terms that have x's in them are the x minus a to the k. So differentiating pulls the k in front, subtracts 1 from the exponent, and I run from there. And you'll notice I have to start from essentially 1 here. I have to be a little careful there. It should actually be, I'm going to go from 0 here. So going from 0 is a little bit weird, but you'll notice the 0 in the k there is going to be fine. It's just 0. That first term is gone. The constant term is not there. And so I get k, ck, x minus a to the k plus 1, k minus 1. And so I subtract 1 from the exponent, and then I do that. I could reorient this thing to start at x equals 1 or k equals 1, in which case I would have to sort of fiddle with some of these subscripts, right? So doesn't matter at this point. The k equals 0 is going to sort of knock out that k term there, so it's going to converge. Now this will converge on the same interval that the original one converged on, so that's sort of nice. All right, and finally, we can integrate these things as well. So to actually integrate this, I just integrate each term. And again, the only thing that has an x in it is the x minus a to the k. The antiderivative of x minus a to the k is just x minus a to the k plus 1 over k plus 1. And you could sort of do like a u substitution in here, but since u is just x minus a, well, du is just dx. I don't really get much difference there. It just sort of replaces that x minus a with a u, and then I go back to x minus a, and it works out. So I can integrate this thing, and the indefinite integral has a plus c, that constant term. So it's not a unique function coming out of it, but the power series part of it is sort of a unique thing. It's kind of nice. Okay. So what we can do from this is fairly powerful, actually. We can sort of talk about things like sine of x and cosine of x as infinite polynomials. We can get from one to the other by differentiating it. So if I differentiate the power series of sine related to sine, I would get cosine. So taking the derivative actually does give me cosine, which is kind of amazing. We'll sort of see that next time as well. And then integrating sine would give me a negative cosine of x. And so I would sort of get an opposite signs throughout, but I would have a cosine function going through here, which is pretty great. So next time we will talk about these sort of Taylor series. And so that's going to be talking about these power series, but based on those Taylor polynomials we talked about last time, and then sort of how they converge, where they converge, what functions have Taylor series expansions, all that kind of fun stuff. All right, cool. So I'll see you next time.